We'll start discussing things further. So in the last lecture, what we have studied is the specification of the linearity, right? So linearity is nothing but the deviation from the standard curve that is designed for the measurement system. So that deviation can be expressed in terms of, say, so it's 10 o'clock, only 57 students have joined till this point of time. It means half. Right. Okay, so in actual practice, the difficulty is there for expressing this linearity error or linearity specification. The reason very clear. Many times the deviations that we find, say the curve designed is suppose a straight line between the input and the output. The actual reading may be somewhere spread about this line. So it can be on one side or on the other side. And the characteristics are found by having a line which is passing through in between. So there are difficulties in specifying. So how to consider the linearity of an measurement instrument or measurement system? right? So there are many possible methods of expressing that, and that is the major difficulty. Which one is to be taken perfect, or which one is taken as a standard one? That is very difficult to know, right? So there are difficulties in expressing the errors, and the difference arises in the way which the ideal or a best fit straight line can be set up. Say, for example, through the measurement, I am only knowing the spread of the different readings. So the line can either pass through zero, or it can be, say, the best fit line whichever passing through some intercept. Say, for example, this intercept C, or it can be between, say, the full range of the measurement that covers the very first reading and the last reading, and the line shall pass in between these, right? So there can be different ways with which it can be expressed. So there can be differences in which the ideal best fit line can be set up, and thus the line positioned by the usual calculated statistical averaging methods of least fit or some other way forms a line fitting calculation, and are also used in different fashions. Say, for example, the readings that might be obtained for the particular measurement. Say, for example, the red dots I am showing on the line. So one can have a very smooth line passing through the readings that we actually obtained for the output to the given input, and on joining the actual performance curve can be found out. So the best straight line is to be obtained depending on the different criteria, right? So based on the different criteria, we are going to obtain the desired say straight line, and then we are going to find for any given input. Say, for example, this input number, some value, say input 1, 2, 3, 4, 5, this is 6, let us say sixth input, and we go on finding the deviation from this standard line with respect to all the reading that you have taken. If wherever it stands maximum, say for example it is 1 here, the second here, but on comparing all, we find, suppose it comes maximum on the sixth reading, the difference between the sixth reading and the corresponding point on the straight line, the best fit straight line, we find that it is a worst deviation. That is nothing but the worst possible non-linearity into the instrument or into the measurement system, right? So this yields a smallest magnitude of the error calculation for the various kinds of the line fitting, but may not be appropriate. Now, why it is not appropriate? Because few of the readings are there which are say beyond the line, which cannot be, say, very faithfully representing the actual performance, nowhere related to the best fit straight line, right? So there are different strategies or different methods of specifying those. So those can be, now, say for example, the one best fit line can be made to pass through the zero irrespective of the readings. Say for example, even if none of the reading is corresponding to the initial very zero reading, still we will try to make the best fit straight line to pass through zero. This is one specification. So, and then we find the linearity error. I think that we'll see how the error are specified, but now it depends on the different references. The first line is passing through zero, the best fit line can pass through zero. Then second, the line can be between the expected 0% and 100% of the point. So irrespective of the reading in between, I'm going to take the very zero first reading and zero the last reading, and I'm going to draw a straight line in between that. So in this condition, any issue, Aditya? Are you there? I think you are trying to call me. Aditya, are you there? It is now 10:07, and at 10:07 we are having only, say, 57 students there in the class. At 10 exact, right? That's what I told. Nearly half of the students were present at 10 a.m. And now, at the end of say 10:07, at 10 a.m., we are having 109, and still few are on the waiting. Is not the one that we expect. So this includes 2 scholars also. The 2 PhD scholars also included into this one. Aditya, you want to say something? Are you there? Aditya? Your class representative, is he there? Okay, so I think we'll continue for the discussion. So the line can be between expected 0 and the 100% of the points, and there can be a line passing through the most number of the readings. Suppose now there are total 20 readings, out of which few, say 10 readings are above the line and 10 readings are below the line. So we try to draw the line so that it is having equal number of points above and below the line, and we draw the theoretical line. The theoretical line need not to be in the best fit curve, but it is taking care of say number of readings above and below the line, like that. So the theoretical line is not necessarily one of the above, but it can be said that we have found the say best fit line, or say the straight line characteristics of the instrument, and then we can find out the deviation, the maximum possible or worst possible deviation, then we can specify. Now generally this is specified in terms of the error. Say if I'm going to find this deviation, let us say del D between for any of the input, say it is the worst possible deviation, that is say del D, and then we find out this del D over full range or full scale, I say full scale reading, and then we express that in terms of the percentage. So we call the percentage linearity error in terms of del D over full scale reading, and then we express that in percentage. So this is how the linearity error is expressed. It's a very simple way to express. But I think this we have seen somewhere. Deadband is defined as the largest change in the measure end. Say for example, you are starting your vehicle from 0. You won't find any deviation on your speedometer unless it catches certain speed. Let us say that speed at which it is showing some deviation. Say for example, it is a 3 km per hour or 4 km per hour. Is the minimum speed when taken by the vehicle, it is going to show some deviation on your say speedometer. So that is called the deadband. So this is nothing but some input that is consumed for overcoming the inertia of the system. So that is called the deadband. I think this we have discussed somewhere. Right. So it is the minimum value of an input that is consumed or defined as the largest change in the measure end to which the instrument does not respond. Right. Then we come to the hysteresis. In a similar way, we can say that the hysteresis is there. So in the hysteresis, what we find, the magnitude of the error caused in the output for given value of the input. There is deviation. Say for example, this the upscale reading and this is a downscale reading. So while showing the ideal expression required, suppose it's a straight line somewhere like this. So ideal line or ideal instrument characteristics. But in the upscale reading, we find that it is going to show some deviation. There is some non-linearity induced. And once we go to the maximum value of the input and corresponding maximum value of output is found out, and then when we start reducing down the load, it is going to exhibit some other lag in the property. So there is some higher reading shown than the actual value or ideal, than the ideal value. So in this condition, we find that this is an error. So this is maybe because of, it happens maybe because of backlash. Say for example, there are gears, and say in the gear, say the teeth of the gear, the second teeth, and in between there is one more teeth, meshing teeth. So this is nothing but a play that is available. That is because of this one, this motion of wheel number 2 is not going to have any further transmission, that is because of backlash. Then it can be because of elastic deformation. Say for example, the elements will undergo deformation, and unless it is say taken completely because of the flexibility, it is not going to show any say motion transmission from one point to the other. Say take an example, say for example this is a flexible component, and now these are this is lever 1, this is lever 2. I want to transmit motion. You can see this one now, it is touched, and say it is taking some motion, and then after it starts moving. So it's because of elastic deformation. The similar thing can be seen in the magnetic characteristics. I think this you have gone through the electrical engineering in your earlier studies, even in the 12th standard or so on. Then there can be friction. We know that the friction at the rest, so starting from the rest, is generally higher than the friction that is between the two parts which are already moving in motion, right? So this friction can also be the cause for this. Then there can be some internal friction, and then time varying relationship. Say this is something that is a dynamic response, but that occurs over a large span of time. There can be wear and tear and the different components that are introduced after the consistent usage. So these are the reasons. These are the elements that are going to affect the hysteresis, right? So now still I find there is one student who is trying to come join the class. Okay. Then hysteresis effects are eliminated by taking the observations. Now it's a very simple way to know how much error is there or how much deviations are occurred because the hysteresis can very simply found out. Say I go on the experimentation and take the reading, so that upscale reading and downscale readings are taken, and then characteristics is plotted, and then what is the simple method? I take the average of this, and then I can have an ideal line passing through this, which is going to indicate the behavior, the true behavior or the ideal behavior of the measurement system, right? So this is how is told. Hysteresis effect are eliminated by taking the observations both for ascending and descending, upscale or downscale reading values for the input, and then taking the arithmetic mean, this simple way. I think this is clear to you. Let us understand what is backlash. I think I have very roughly told. Say for example, this is a gear profile, and into the gear profile there is some mismatch. This is another gear, and because of this you can see the profile. There is a difference between some on the say pitch circle diameter or the mean diameter. You find there is a difference between the shape. So it means that unless otherwise this deformation del is covered, no further motion, no contact between the teeth 1 and teeth 2 is going to occur. It also means that teeth 2 will not start any movement till this slackness or this gap is bridged up. So this is defined as the maximum distance or angle through which, if I am going to see this in terms of the angle, the center, at the center of the gear, then corresponding to this deformation del, there will be some angle. Say I can call this as del theta. So it is defined as the maximum distance. There is length in terms of del or some angle through which any part of the mechanical system may be moved in any one direction, and which is not going to result in any positive motion of the mating part, that is part number 2. That's what is told here. So it is, say, the phenomena that can be seen here. Say it takes certain time to have the engagement. Say unless there is some del, the two parts come in contact, the input is consumed here. Now this is a condition when part 1 and part 2, gear 1 and gear 2 are not in mesh. We have started giving input. So this is the initial input. Say I call this the input 1. Input 1 is consumed till part 1 touches the part 2, or the gear teeth 1 touches the surface of gear teeth 2. Then when I am going to give the further improvement or further displacement, further motion to the part 1 or gear 1, it starts giving the output. Now when I reverse the direction, say from the counterclockwise, now I go to the clockwise. So this is for counterclockwise motion. This is the behavior for counterclockwise motion. When I start moving from counterclockwise to sorry, the clockwise to counterclockwise, sorry, clockwise to counterclockwise motion here. Again, it starts the minimum, say, motion corresponding to del or del theta, so that there is no motion of part 2 again. Say for example, now I am first moving in the clockwise direction. Now as I am starting moving counterclockwise, you can see motion of part 1. This finger is now taking the moment and now it has touched. So the distance or the instance of disengagement and engagement again with the part 2 is here. So it is going to consume some input, and then it will start taking the motion. Further, it can be extrapolated, and then we can find that this is the input consumed during upscale reading, and this is equivalent to this parallel now. So this is equivalent to the input that is consumed in the downscale reading. Say I call this as input 2. And then total hysteresis will be because of the input 1 plus input 2 that is consumed to overcome the gap between the two mechanical meshing components, or the two mechanical meshing parts, right? So input output characteristics are similar to hysteresis. Into hysteresis, what happens? The curve is little modified, but here it is a sharp and having a clear start and end for the input that is required to overcome the backlash. So error can be minimized by taking a very close tolerances. Now how that can be minimized? I will have proper selection. The gap should be such that it is exactly equal to the tip profile. And then in this condition, even small motion in my finger number 1, will result in motion of the 2 at both way, clockwise as well as counterclockwise direction. So this is very clearly understood by understanding the gear phenomena, right? Then there is dry friction or backlash. The dry friction also going to take the same role. Say for example, there is surface, and on this surface I have got an object on this surface. Now if I am going to apply some force, unless otherwise the friction is overcome, I need to apply the force. So input is consumed, but once you start moving, it will require lesser amount of input. So it is defined as the maximum distance or angle through which any part of the mechanical system may be moved in one direction without causing motion to the next part. But this is occurring because of the friction or the dry friction, right? So this is exactly similar to the hysteresis or the backlash effect, right? So I think the overall hysteresis can be found out. So numerical value is specified in terms of the output. I have already told you. Similar to the linearity, this is also specified in terms of the percentage of the full scale. Say for example, now for any input, let us say this is some input that is going to have the maximum deviation here, the maximum hysteresis. Then I find for this input what is the value of output maximum, and this is output minimum. And then I take the deviation of output.
Excuse me, sir.
Yes, please go ahead.
Sir, some of the students have got disconnected. Can you please allow them?
What are the reason you told why they got?
They got disconnected due to network issues.
Okay. So this then we are going to express this or the deviation over the full scale. Say for example, the maximum reading, the maximum input that I am going to give here, if it is known, the full scale reading of this instrument is known, we can find out this as FSR. Exactly similar to the specification of the linearity. Then we express that in terms of percentage. So overall hysteresis can be expressed in terms of, or hysteresis error can be expressed in terms of the deviation of the output for the worst. I am saying the worst deviation in the output over the full scale in terms of the percentage. Okay. So hysteresis effects are eliminated by taking observations both. I think this we have discussed both ascending and descending or upscale or downscale reading, and then we take the arithmetic mean. Any doubt regarding these properties? Anything that is not clear? Please let me know anything that you want to discuss here. This is very simple and very standard approach. You can find that in any of the textbook. Even there are numericals given You might have gone through this numerical somewhere else also, especially in electrical engineering and so on, right? So you are required to go through the textbooks. Okay. Then I think this is a generalized graph for input-output relationship where the hysteresis is present. The hysteresis loop for constant magnitude cycles, say upscale reading, then downscale reading, then coming back again. And in this way, you can see now the full extension of the input variable can be found out. This graph I had taken from the book of Handbook of Mechanical Measurement. I think I have referred that earlier. Page number even also have been given. So this is generalized graph for input-output relationship where hysteresis is present. Right. So I think we are not going to discuss right now. So the portion that is shown in the dotted line. We assume that the process is consistent enough. Okay. So this indicates the upscale reading both way, and this indicates downscale reading. Then let us understand the drift is defined as the variation of the output for the given input caused due to change in the sensitivity of the instrument. Please pay attention here. Sensitivity change of the instrument due to certain interfering inputs. Maybe because of the temperature change, maybe because of the component instability, maybe because of humidity. There can be some electronic instrument which has got the heating effect. I think I referred that to you, valves, where there is a filament, and over the issues of the equipment, electrical instrument, we are going to find that heat is emitted, and the temperature, change in the temperature causes change in the operating characteristics of the valve. So this is going to produce the drift. So drift is nothing but deviation. The simple synonymous word is a deviation. Now deviation in the characteristics from the ideal one. What is the ideal characteristics we desire for most of the linear instrument? It should be this one. It is going to drift. Either it will shift over, or it will shift down, or it will have some other thing here like that. So it is a drift or a deviation. There are different reasons for deviation. So error can be minimized by switching the instrument. So for example, if this is the case where the instruments are going to have some kind of current flowing through it, and over the period of time, because of the current flow, there is change in the instrument characteristics or the component characteristics, then we try to start that early, say sometime early before the experimentation. So temperature of all the components are stabilized between this time of 30 minutes starting before the actual experimentation, and then it will be stabilized. All components will start working and in the stable condition, and thus the drift, this kind of drift can be minimized. Right. Now there can be some environmental effect, like say all calibration and specification of the instruments are only valid under control condition. This is what I had told you earlier. Say for example, the standards that we have say agreed upon with an international agreement, those standards are derived at a particular condition of temperature, pressure, humidity, and so on. But the measurement that I am taking in this room are having some different conditions than that of the ideal conditions. So because of the change in the condition, there is effect. Right. So there is change in the temperature of the ideal element and the actual place where measurement is taken. So the standard ambient conditions are usually defined in the specification. Say for example, typical instrument specification and measurement system specification, if we read from the manufacturer's catalog, they require that the measurement is taken in control ambient conditions. Say there is no air velocity, there is proper humidity maintained, temperature maintained, pressure maintained, and so on. As the variation occurs in this ambient temperature, pressure, etc., certain static instrument characteristics are going to change. It is bound to have. And thus the sensitivity of the instrument or the measurement device or functional blocks is going to change. Is going to create disturbance in the magnitude of the output shown by the instrument. Such environmental changes affects the instrument in two main ways. The first is called as zero drift, and the second one is called as sensitivity drift. Say zero drift, sometimes known as, sometimes is very equivalent to be called as a bias. Right. So Now let us understand what is zero drift. Zero drift is the instrument zero is shifted. I think in earlier discussion I have shown you the example of the micrometer screw gauge. The micrometer screw gauge is having some kind of the value shown. Say for example, when this movable jaw is very close vicinity with the fixed jaw, instrument reading is shown, say some value 0.02 mm, suppose. It means that zero has been shifted. So this is something similar to the bias. So zero reading of the instrument is modified or shifted than the ideal place due to ambient condition or maybe because of the operating situations. That is called a zero drift or a bias of the instrument. So then it causes a constant error. I think this we have discussed. Say now if I am going to put the block here of different dimensions, say 2 mm, 5 mm, 10 mm, the respective reading will be 2.02, 5.02 and 10.02. That is the meaning, a very simple meaning, that zero has been shifted. So it causes a constant error that exists over the full range of the measurement of the instrument. Right. So it is seen here. The nominal characteristic or ideal characteristics here, but characteristic with zero drift, say output. So it is a pressure and the scale reading. It is going to show some scale reading. Instead of showing the pressure at pressure 0, it is going to show same reading. The scale reading is this one. So it is something opposite to the dead band or threshold. Right? Dead band and threshold are the characteristics where the initial input is consumed. But here it is going to show some output even at zero input. At zero pressure, it is going to show some pressure on the scale. Right. Now, I think this we'll discuss in some next slide. Then the sensitivity drift. Let us say that the sensitivity is going to change. What is the sensitivity? Is nothing but the relationship between the input and the output. Say for example, the relation here, nominal relation is for given input, I should have the value of the output here. That D should remain constant. So this is what is said or this is desired, that at any point of the usage, the relationship must be constant, output to the input. But now it is going to shift. Then the constant 1 to constant 2. This is now the new or modified characteristics of the measurement system having constant 2. It was desired with constant 1, but now it is going to exhibit the proportion like constant 2 is there. If I am going to take the input output for this curve, it will have constant 2 or K2 we can say. So this is what is defined as amount by which the sensitivity of an instrument varies as ambient condition changes. So this is what is shown. Say if the instrument is not having any zero error or the zero drift or the bias is zero, ideally it is required, but we find in actual practice is going to shift over. Right. So this is called as a sensitivity drift. So the total effect of the drift or change in the instrument characteristics or the measurement system characteristics is addition of the sensitivity drift plus zero drift. Now let us understand the readability of the scale. Say simple element is shown, a pressure measurement device is shown with the scale reading in terms of the bar, black color scale and red color scale with say pound per square inch. Now what is the readability? It is important for analog instrument. It's very obvious. It is the closeness to which data can be read. So let us understand based on scale only, the display panel only. The display panel here of this instrument is say black pointer or white background, and there are some graduations shown, say graduation 1, graduation 2 and so on. So how I can interpret the information over the scale, that is the readability. So it depends on the scale of measuring device and the observer. Now it is preferred to give that in decimal rather than the fraction. Say it is not shown here that between this 500 bar and say 1000 bar, we are not shown anything as say 700 point something bar. It is not shown in terms of fraction, but it is represented. It is decided. It is desired that it should be represented in like 1/4 or one half and so on, so that it gives better readability, better approximation to the reading, right? So for better readability, the measures can be taken. What are the measures? We can plan. We can have the proper magnification factor, proper scaling, proper amplification, and so that we'll have better and very clear readability of the instrument, right? So the next term is very related to the readability. Span. Span is nothing but the range of the say range of the variable. Say for example here from 0 to 2500 bar is the value that is shown, or in terms of psi, the last value that can be shown on the scale is known. So it is the range of the variable that an measurement device is designed to measure, that is called a span. So there are definitely two limits, or the two minimum and the maximum limits of operation. So low and high limit will be there. So it is called a linear operating range. It has got a linear operating range. Then it is sometimes related to dynamic fidelity, or fidelity called as a dynamic range. So dynamic range is nothing but the largest to the smallest dynamic input, largest by the smallest dynamic input. Right. So I think this will again pay attention into the dynamic characteristics. So span of this equipment, or the pressure measurement device, is from 0 to 2500. Span is nothing but a maximum minus minimum, say 2500 minus 0 bar. That is nothing but equals to 2500 bar. This is a span. And range is from 0 to 2500 bar. I think these two words are very simple and very say interchangeably used to represent the characteristics of the instrument. That is the minimum and the maximum range between which the instrument or the measurement system can be used for measurement. Any doubt in understanding the span of the equipment or the device here is 2500, and range is between 0 to 2500 bar. If it is clear, then we'll move ahead. Now the tolerance band, it is the highest allowable error. First of all, we must understand what is the error that is specified in terms of the certain value during measurement process. Say now the measurement process is carried out and I am going to get some readings a random way spread like this. Say this is now reading 1, 2, 3, 4 and so on. So what I have done is, or we have done is, we have found out the ideal line that is passing through this. So let us say this is the output and this is the input. Between output and input, we have obtained a best straight line to represent the characteristics. Now the error can be found out. Say for example, this is the reading number 5. So error can be found out as a deviation above this line. Say I call this as del 5. Then say this is sixth one. So I can find here the error number 6 or error 6 at the 6th reading, and likewise I can find. So wherever del maximum is going to occur on either side of the line, say del max above the line, and there can be something del max below the line. I'll call this del max 1 and del max 2. Then I can very clearly say that the tolerance band is plus this value and minus this value. So what is the error? Let us say now, say coincidentally the value appears to be the same. Say value of plus del max or del max 1, let us say it is 0.2, and also minus del maximum 0.2. Then we can say that tolerance band for the instrument error is plus minus 0.2 units of the particular measurement. See, if it is pressure, then you can call it as a bar. If it is temperature, you can call it has a degree Celsius, and so on. I think this is clear to you. The highest allowable error that is specified in terms of certain value during the process of measurement is called a tolerance. And now we are going to express that in terms of percentage of the full scale. So I am going to find this as del max over the FSR, and then I am going to express this in terms of percentage. So it is nothing but a percentage tolerance. Right? Then it specifies designed accuracy limits. So where from this has came? What is we have analyzed here? We have gone through the different measurement. N number of measurements are taken, and we have found the characteristics of the instrument by having the error quantified at the given inputs. It means that throughout the process of the measurement, we have found what is error and we have determined the accuracy. Now, what is the maximum extent of inaccuracy that can be present or within which the instrument is accurate? That is what I have found out in terms of plus del max and minus del max. And then I express that in terms of the percentage of full scale reading. So tolerance band is nothing but one that specifies the accuracy limits of the instrument or the measurement system, right? Anything that is not clear at this point? Okay. Now pay attention now what I am telling you. Beyond this, there are many static characteristics of the instrument, and those are introduced into the system because of multiple electronic components that we are going to use. See, if you go back to the functional block of the instrument, we have said that there is a primary sensing element, the variable conversion element, variable manipulation, and so on. The block, the functional block of the instrument from input to the display. Now, at each and every point, if there is some circuit that is used for magnification or some other kind of interpolation or interpretation, say processing between the signals, maybe required signals are amplified, magnified, amplitude can be changed, the frequency can be changed, and so on. Because of which there is going to have some kind of characteristics in the instrument that we are going to study hereafter. A very brief discussion on this will be there. So that is sometimes called as a rectification either, or saturation, or crossover. Now, let us understand that now this is a VC, variable conversion element, and then we discuss this. Input to the VCE, let us say the VCE that we have shown in earlier block diagram. Input is a very linear. Say for example, there is a spring, and then the deviation of the spring is going to give the deformation del. Now that deformation is taken by VCE. Say for example, some electronic device is there, which is going to magnify the given proportion. You can see it is magnified. So input to the VCE is magnified to have better reflection of the signals at the output. So one part of the VCE is going to act as a amplifier. So in this amplification process, not all the input values from this are magnified, but there is a change in the magnification approach. Because of the instrument itself, the amplifier characteristic itself, it will transfer or it will magnify certain extent of the input properly, and then there will be some non-linearity in the amplification. Say while magnifying, let us say this is half of the reading. Till this point it has worked properly, it has magnified this value, but onward it is going to have some distortion. It may be because of the amplifier characteristics itself, which we have not designed, but unintentionally it has entered into the system. Now these are the situation where we are going to come across this kind of static errors. So the real system blocks will sometimes have input signal levels that are larger than the allowed. So he can see it here. Now we have made it purposefully large than the actual input that we have supplied to one of the stage of your say functional block of your measurements instrument. So if the signal form is not amplified faithfully, the output will not have the same linearity neither the linearity nor the characteristics will remain same. It will have some change in the characteristics. So a varying amplitude input signal, such as the steadily rising linear signal shown in this figure, will be amplified differently according to the gain or the amplification factor or amplitude curve of the block. So in this condition, we can find that the uncompensated electronic amplifiers, say if the amplifiers are not properly designed, the large amplitude are usually less amplified. Say for example, onwards, here, the remaining half-wave signals at the input will be amplified disproportionately here. So large amplitudes are usually less amplified than the median points. So it is amplified properly here, it is not properly amplified onwards. So this kind of elements will be then called, say for example, an AC waveform. The different levels of the cycles of the signal may not be all amplified equally. You can refer this earlier. There will be some difference in amplification. Half signal will be amplified properly, remaining half will not be amplified properly. So here what is called? Then the basic electronic amplifying elements are only able to amplify one polarity of the signal. So now it may happen that only one polarity, say for example, the signals which are appearing either on this side or on this side will be amplified properly, and the other one will not be amplified in a proper fashion. So this is what is going to happen. Say for example, the amplifier, if it is having a property of a single polarity amplification, it will amplify only one part, that is shown here. So part 1 is amplified here, part 2 will not be amplified, and then here there will not be proper signals, right? So this is called as a rectification. So that is what, because of the process, we find that it has rectified the lower half. The signals are rectified. This is one of the deficiency that has incorporated into the system, that is called as a static characteristic. This will remain permanent over the full range of the measurement. Say for example, your pressure measurement device at some phase is consisting of this kind of amplifier, and if the amplifier is not carefully designed and it has got some error like this, it will always show some reading amplified and shown on the display panel, but remaining signals will not be shown. So that is called a rectification error. Signals are said to be rectified. Similarly, the signals, if it is at the input is having this kind of waveform, AC waveforms, if the signal is too large, the top is not amplified. Say now, beyond the range of the amplification, the input is given, say starting from 0, say for example, it is possible to amplify, but at certain point of time, the amplifier will not be able to sense the signals above this level. Unless it comes back here, it will not sense. So the conversion of the signals from this to this will occur, whereas this will be left over as it is. And then you can find the output signal at that particular functional phase will be representing this kind of signals, right? So these are called as saturation. We are going to saturate because of the instrument characteristic. There is saturation limit of the amplifier. Signals above these zones are not at all detectable, right? So it's called as saturation. So this is a saturation line. It can be say well near or it can be very near to top, but then definitely it's going to have some saturation. So as with many physical effects, the effect is sometimes deliberately invoked in circuitry. They maybe unintentionally. An example here, it is used as a simple means to convert the sine waveform signal into the square waveform. The waveform is changed now. Instead of sine, it will be more or less a tooth type, or say kind of more or less rectangular type. So it will be square waveform. You can see that is more approximate to square format. Instead of the sine wave, it is going to be like a say rectangular waveform. Okay. Then similarly, the signal passes from negative to positive polarity in the distortion is evident. Say for example, now it is a bipolar amplifier in your phase of VC, there is one part into the VC which is acting as an amplifier, and input signals are in the form of waves, sine waves, then it will have some distortion into amplification. So for example, the signals will be amplified, but it is going to take the chopping off of the signal. So ideally it is required to show the signal in this format, but it has shown something less. Okay, so this is called as a crossover. I think that is very evident. This is called as a crossover. There are few more, I think, but why we are not dealing, let us understand this. Why we are not dealing this into instrument characteristics? Because this is a part of your instrumentation, or say part of the functional element design. So there are many reasons by which the output of the measurement system is not going to faithfully represent the true input that is supplied to it. Okay, so this rectification, saturation, crossover, and few more things which are there because of some circuitry or some inherent parts of your functional blocks, those are very carefully to be detected and eliminated. But mechanically we find it is beyond the way of calibration. And that is why you find in textbook this is not discussed in much detail. So time being, we are going to say not paying attention to this kind of static characteristics like rectification, saturation, crossover, and few more things are there. But we are going to concentrate only on the things which are shown in the blocks in the initial, say, accuracy, precision, bias, linearity, hysteresis. These are the, say, major important mechanical properties which we concentrate on, and we try to find the solution over that through the process of calibration. So whenever we will be dealing with the numerical part of your static calibration, majorly we are willing to find out the behavior or deviation in the behavior of the mechanical measurement system. Right. So I think with this we'll be able to say conclude our discussion on the properties. Now we'll see a few of the numericals, or say the treatment that is required for knowing the static characteristics. Say for example, range, specification of non-linearity, specification of hysteresis, and now you can correlate this with the things we are studying in the practicals. What was asked to find accuracy, precision. Okay, these were the things to be found out. So we'll carry out discussion on this then in the coming class. So there will be a very short discussion, and now you are required to go through the textbooks to find varieties of the numerical, the treatment that is given. Say for example, there is a single input given to the measurement process, and there can be n number of readings taken at output, or the n number of readings are observed. Then what are the different properties we can find out with respect to these observations? How the error can be found out, how the bias is found out, what is the random error, how the random error is found out. Those are the things we need to see in terms of the numerical applications. Say, solving the numericals we must go through. Our test number 3 will be based on this, to identify the property. So we should be in a position to calibrate the output input characteristics of the instrument with the given input values we should be able to give. Say for example, there is some data, some table you have found for input values, and there are some output values, and there are n number of readings, say starting from 0. So there are n number of readings. For the same input, what is the output shown in the as a first reading, and so on. So based on this, one can find out the spread. Say this reading 1, 2, 3, 4, 5, 6, 7, 8, and so on, the nth reading. And then we can find out the mean. Using the statistical method, we can find the best estimate. Then we can find out what is the maximum deviation for, say, for example, 8th reading. Let us say this is the 8th reading. We can find what is the deviation of this, or what is the error at the 8th reading. Similarly, we can find at the 9th reading. Then we can have different interpretation. We can find out range, we can find out tolerance band, the span, the random error, the precision error, and so on. Now, the second way of expressing, say for input, we are going to find the output. Say for example, the other table. Now, in this one, we applied a constant input for n number of times. Now, this input is gradually varying. So the output is noted so that there is change. For input 1, there is output 1. For next input, it is going to have output, means we are going to have n number of different input. Now in this condition, the property can be found out, say first reading, second, third, fourth, fifth, and so on. I think you are able to see this one. Then we can find the best fit line, maybe with regression analysis, or maybe a simple straight line taking the n number of readings above and n number of readings n by 2 above and n by 2 on the down scale of the below this line, and then we can find the error, and in this condition we can find the specification of the linearity, non-linearity, and so on. The third way is we are going to apply the input and output in the upscale as well as the downscale, the same reading. So for example, upscale reading, input is given, output is noted, and then coming in the reverse way, the last value of output, and then we are approaching to 0, upscale and downscale. So in this condition, we are probably about to get the spread like this, and then we'll be able to join this and get the smooth curve called as hysteresis. Then we can find out the characteristics. Okay, so these are the simple ways in which we can find out the behavior of the system or static characteristics of the system can be found out. So we'll discuss this in little, say probably only one class will be sufficient for discussing this. But there are very simple numericals given in all textbook. You go through any of the Indian edition, the foreign author edition, and so on. You will find good number of numericals are solved. So once you go through, I will ask you to start writing your journals also. Okay. Any doubt till this point? Let me know, please. Okay. Now let me know if there is any. I think one more class we are going to have tomorrow. Yes, we'll be able to finish up that tomorrow. Good. So then in the next week we'll have a test number 3, probably on Monday. Monday evening we'll be able to take the test, and the test will be based on the static characteristics only. And also I will ask you to submit the journals now. Write the journals and submit the journals in the next week for all the 5 experiments. I am again iterating. If somebody want to come here and perform the experiment with their own hand and take the reading, they are welcome. They can come. A limited number of students can come and they can have the readings. Otherwise, the readings from the video can be taken for writing the journals. So I think we'll stop here for today. Thank you for joining.